Copper mining starts with extracting copper ores, such as chalcopyrite and malachite. Mainly mined in regions like Chile, the United States, and Zambia. The extraction method is determined by the ore's depth. Open-pit mining is employed for shallow deposits, using large-scale machinery like excavators to dig through surface layers, and massive dump trucks to transport the unearthed ore. For deeper deposits, underground mining is utilized, employing drill rigs to create deep holes for blasting, breaking apart the ore body for extraction through tunnels and shafts. Once extracted, the copper ore undergoes initial processing, which involves crushing and grinding. This is accomplished using heavy machinery that pulverizes the ore into smaller fragments, enabling the separation of copper minerals from the surrounding rock. The process typically starts with jaw crushers or gyratory crushers that break down the ore into smaller chunks. These chunks are then further ground into finer particles using ball mills or sag mills, preparing the ore for the next as it increases the surface area of the ore, significantly improving the efficiency of subsequent separation and extraction processes. Next, the copper ore undergoes the concentration process through froth flotation. In this method, the finely ground ore is mixed with water to form a slurry, to which collectors and frothing agents are added. The mixture is then agitated, and air is injected into it, which helps the copper minerals attach to bubbles and float to the surface, forming a froth layer that can be skimmed off. The gangue, or waste rock, settles to the bottom and is removed. This results in a copper concentrate that typically contains 20 to 30% copper, along with other minerals and impurities. The concentrated copper ore is then moved to the smelting process, where it is heated in a furnace at high temperatures. During smelting, the concentrate is mixed with silica, and air or oxygen is blown through. This causes the iron sulfide in the ore to oxidize into iron oxide and sulfur dioxide gas, which escapes into the air. The remaining molten material, known as copper matte,
contains roughly 50 to 70% copper, along with iron sulfide and other metal sulfides. The final step in the production of pure copper is refining,
typically done through electrolytic refining. In this process, the copper matte is cast into large slabs, which are used as anodes, in an electrolyte solution of copper sulfate and sulfuric acid. When an electric current is applied, copper from the anode is dissolved and deposited onto a cathode, while impurities either fall to the bottom or remain in the solution.
This results in 99.99% pure copper at the cathode, ready for industrial use. This method not only produces high-purity copper,
but also allows for the recovery of precious metals like gold and silver that may have been present in the ore. Following the electrolytic refining process,
the copper is transformed into its final physical form through casting and rolling. The purified copper is initially melted and then cast into
large rectangular slabs or billets. This casting process involves pouring the molten copper into molds where it solidifies. These slabs or billets are then ready for further processing into usable copper products. The next phase involves rolling the copper slabs to achieve the desired thickness and mechanical properties. The rolling process is conducted in two stages:
hot rolling and cold rolling. During hot rolling, the copper slabs are heated to a high temperature to make them more malleable and are passed through a series of rollers
that gradually reduce their thickness. This stage is generally used to produce copper plates or sheets that are relatively thick. Once the hot rolling is complete, the copper may undergo cold rolling, performed at or near room temperature, that apply more pressure than those used during the hot rolling process, further reducing the thickness of the material. This stage provides a finer surface finish and enhances the hardness and durability of the copper, making it suitable for precise applications. Plates that require tight tolerances and smooth surfaces, such as in the manufacturing of copper wiring and electronic components. The final product is typically wound into coils for ease of transportation and handling in subsequent manufacturing processes. After copper has been rolled into thin sheets or coils, it undergoes further transformation into copper wire through a process known as wire drawing. This involves pulling copper rods through a series of progressively smaller dies or molds to reduce their diameter and extend their length. The copper starts as a thick rod, and each pass through a die reduces its thickness, ultimately turning it into fine wire. This process requires significant force, and the copper must maintain its structural integrity as it is stretched into longer, thinner wires.
Following the wire drawing, the copper wire undergoes the annealing process, which is necessary to restore the ductility lost during the drawing.
Annealing involves heating the drawn copper wire to a specific temperature, then allowing it to cool slowly. This heat treatment relieves the internal stresses caused by the drawing process and softens the metal, making it more flexible and easier to work with, which is a critical property for its use in electrical wiring and electronics. The combination of drawing and annealing processes
ensures that the copper wire is not only structurally sound, but also possesses the necessary electrical properties for efficient performance in a range of applications.
from household electrical wiring to sophisticated electronic components. After the copper wire has been drawn and annealed, it moves to the next essential stage:
insulating and testing. This process involves covering the copper wire with materials such as PVC,
polyvinyl chloride, or Teflon. PVC is a versatile and flexible plastic coating that provides excellent insulation
and is resistant to fire and chemicals, making it suitable for a wide range of electrical applications. Teflon,
known for its high temperature resistance and non-reactivity, is used for insulating wires that will be exposed to extreme conditions. The insulation not only prevents electrical leaks, but also protects the wire from environmental factors that could cause degradation or short circuits. Once the wires are insulated, they undergo a series of rigorous quality control tests to ensure they meet all performance specifications. Electrical resistance testing is conducted to measure the wire's ability to conduct electricity effectively without undue resistance, which could lead to overheating and potential failures. Tuners. Insulation integrity checks are also performed, which involve applying high voltage to the insulated wire to ensure that the insulation semi.
In the cable manufacturing process, individual copper wires are twisted or bundled together to form cables. This bundling is essential for enhancing the mechanical strength of the cables and for providing redundancy.
If one wire fails, others in the cable can maintain the connection. The twisting of the wires also helps to reduce electromagnetic,
making it easier to install and route through buildings and infrastructure. Once the copper wires are bundled, additional layers of insulation and protection are applied to ensure durability and functionality in various environments.
This typically involves the application of a sheathing layer, which can be made from materials like PVC,
rubber, or halogen-free compounds, depending on the application's specific needs. The sheathing protects the internal wires from physical damage and environmental factors,
such as moisture, chemicals, and temperature fluctuations. For cables used in more demanding environments, such as
underground or underwater applications, armoring is added to provide extra protection.
Armoring involves wrapping the cable with steel tapes or wires, which guards against mechanical stresses and prevents rodents and other animals from damaging the cables.
This protective layer ensures that the cable can withstand harsh conditions and extends its operational lifespan.
Cables. Once copper wire and cables have been manufactured and fully tested, the next step is packaging and distribution
onto spools or reels, which vary in size depending on the length and diameter of the cable, as well as the requirements of the end users.
This method of coiling not only protects the integrity of the wire and cables, but also facilitates easier handling, storage, and transportation.
After coiling, the spools or reels are packaged for shipping. This usually involves wrapping them in protective materials to prevent damage during transit, such as moisture-resistant plastics or reinforced cardboard. In some cases,
especially for heavier or more delicate cables, wooden reels or metal frames are used to provide additional protection,
as these products often need to be delivered to a diverse range of manufacturers and industries, including electrical equipment producers,
construction companies, and telecommunications providers. Effective logistics involve planning the most efficient routes for delivery to minimize costs and ensure timely arrival.
The distribution strategy also includes managing inventory levels to respond quickly to industry demands,
without overstocking or supply shortages.
The journey of copper continues through the processing facility, where precision and automation ensure quality control and seamless movement to the warehouse.